Welcome back to our adventure covering celestial mechanics as part of the Exoplanet Detection series here in the Cool Worlds classroom. In the first video, we spoke about the importance of Kepler's laws, and in the subsequent video, we even derived the second law from first principles. Today, we're going to complete the story and get the first and third law as well. Now, I know that derivations aren't always easy, but it's critical that we understand where the tools that we are using really come from. You see, exoplanet hunters are just at the end of a multi-century long journey. For example, we will see how these first principles that we are covering now will lead naturally to a derivation of the radial velocity signal. But I believe that it is crucial that we understand where modern methods like that truly originate from. Why? Well, for one thing, it highlights that science isn't just a dogmatic set of facts and figures. Rather, its results are reproducible to anyone who wants to prove it for themselves, as we are doing here today. When we say that the sky is blue but we don't know why, or that the earth is round but we don't know how that was determined, we lose sight of what we're doing. That's not science. That's not understanding. Second, the story of how we developed these exoplanet detection methods is surely not over yet. You might very well come up with a new way to look for exoplanets in the future based off these ideas, but only by mastering the foundations of orbital and celestial mechanics is that clear shining light of revelation going to come through to you. So let's get back to it. So here's where we got to last time. We started with Newton's universal law of gravitation. We then stirred in the second law of motion for good measure, lightly seasoned with some vector calculus, and pulled out from the oven a freshly baked angular momentum integral and Kepler's second law. Don't worry, those pesky first and third laws aren't going to slip away from us though. Let's chase them down today, emboldened by our success so far. In the last video, we obtained this differential equation by the combination of Newton's laws. It relates the radial acceleration and position vectors. We also wrote out r and r dot in polar coordinate form. Throwing the first of these into the differential equation straightforwardly reveals this. But now let's go further and replace the r dot dot term as well, which again is a standard result in vector calculus. Adding this into the mix, we obtain the following more unsightly equation. But a simple trick is just to balance the coefficients of unit vectors. So for the radial direction, that reveals the following. Now this looks like something we could solve, but it's going to take a little bit of work to do that. A common trick for solving these types of equations is to make a substitution. So let's make the substitution that u equals the reciprocal of r. Now since we are working with a differential equation, then we need to relate the derivatives of u and r to each other in order to make this replacement. We're going to start with du d theta and expand it out using the chain rule. We can now put our substitution in place of u, differentiate, and then use shorthand dot notation for the time derivatives. It's useful now to recall our specific angular momentum formula from the last video and replace the theta dots accordingly. We then see that the 1 over r squared terms cancel. So in summary, we have du d theta equals minus r dot over h. Okay, good, but our equation relates second derivatives, so we need another round of differentiation here. So let's keep going. The second derivative is just a nested derivative where that inner term is the one that we just found. So that's just this. Now the r dot term is a time derivative, remember, so it would be more helpful to use times by expanding via the chain rule. We can now see that the time derivative of r dot is r dot dot, and we get theta dot down below. Let's use the same trick from before to remove the theta dot by writing in terms of h. Plugging in directly gives us this, which then simplifies to this equation. We're now ready to plug this into our differential equation. Replacing r dot dot with this rearranged equation, and similarly getting rid of the theta dot with h once again, we obtain the following differential equation in u. Looks a bit messy, but multiplying out that bracket, we see the 1 over r squared terms actually cancel out here. So we have now recast our differential equation in r and time in terms of u and theta. Just for convenience, we're going to absorb all of the terms on the right hand side there into one term, 1 over p. This equation is actually pretty important, so much so that it has a special name known as Binet's equation, named after the French astronomer Jacques Binet, also famous for his work on the Fibonacci sequence. Binet's equation is a second-order linear differential equation, which has a standard solution given by this, where alpha here is a constant of the integration at this point, and theta naught represents the initial theta as a boundary condition. It's convenient to rewrite alpha in terms of p and pull out p as a common denominator, so let's use the replacement E equals alpha times by p. I'm also going to replace theta naught with curly pi here just to align to historical notation. Replacing the u back to 1 over r, we now finally arrive at this equation for the magnitude of the radial vector. This E term is typically called the orbital eccentricity. The polar angle theta is known as the true longitude, and the curly pi reference angle is known as the longitude of periapsis. Cleaning the slate and just looking at that final result, we have indeed derived Kepler's first law, though it might not be obvious. To see this, let's make a polar plot of radial position versus theta. I'll divide by p since this term simply scales the radial direction. We can see that when E is 0, we just have a circle. In other words, the planet is orbiting the star according to the heliocentric Copernican model. But now let's increase the E term a little, and we see that the planet's orbit becomes increasingly elliptical. In other words, non-Copernican. If we change curly pi, we just end up twisting the ellipse round. The position of closest approach is known as periapsis, and so we can now understand why curly pi is called the longitude of periapsis. It's just the reference angle by which we are rotating this ellipse around. The opposite point, denoted by the blue dot, is known as apoapsis. That's the most distant point in the orbit. Now, notice how the Sun isn't at the center of the ellipse. It's offset at one of the foci, just as Kepler told us. We have thus derived Kepler's first law from first principles. We can now see why orbits have to be elliptical and not some other shape. To me, this is majestic. By simply demanding an inverse square law and using a bit of geometry, we've been able to explain the origins behind what Johannes Kepler noted as a purely empirical pattern. We can now see the gory anatomy of our elliptical orbit in full display. We can mark on the radial magnitude r, the longitude of periapsis, as well as the positions of periapsis and apoapsis. Let's make a replacement that f is defined as theta minus curly pi. So that's the true longitude minus the reference longitude of periapsis, and thus f is typically called the true anomaly. Now let's mark on the distance from the ellipse's center to the widest point. In the standard geometry of an ellipse, this is known as the semi-major axis. In other words, it's half the length of the major axis. For completion, I'll note that the other direction is known as the semi-minor axis, b, although we don't need that just yet. Now consider the full width, the distance from the maximum to the minimum radial positions. All we have to do to get this is just plug in f equals 0 and f equals pi into our r formula, and we can see that we get p over 1 plus e plus p over 1 minus e. But we can equivalently state that it must be equal to 2a, twice the semi-major axis. So, solving for p, which I'll leave to you to try, gives us p equals a multiplied by 1 minus e squared. In fact, we can go a little bit further and say that r must equal p when f equals pi over 2 by simple inspection of our radial formula, and thus p denotes this distance marked here. And yes, we've got another bit of jargon for you. This is known as the semi-latus rectum of an ellipse. What a wonderful name that is. Replacing that into our r formula gives us this more conventional equation for relating the radial distance as a function of the orbital true anomaly. As a little exercise here for yourself, try solving and marking on the diagram for eccentricity of 0.5 the f angle that would be necessary such that r would equal a. The only law now remaining is Kepler's third law, which I think has the greatest day-to-day practical value to exoplaneteers. Fortunately, we have all of the tools we need to very quickly get to this now. Let's take these two results that we found in the last slide and move them up to the top of a page of a new one. These are essentially two ways of expressing Kepler's first law. Since both state that r equals something, then of course they must be equal to each other. On the last slide, we related p to geometrical terms, but we also know that p is given by h squared over g m1 plus m2. So equating these allows us to solve for h, and this gives us this big square root equation. The last thing we need to do is leverage Kepler's second law. Recall that it states that dA dt, or a dot, is a constant, which we found to be equal to 1/2 multiplied by h. So integrating over one full period, let's give that the symbol capital P, gives us the area of the ellipse as 1/2 h multiplied by capital P. But we can also just write the area of an ellipse geometrically to be pi a b. That b term, which represents the semi-minor axis, can be related to A and E with a little bit of geometry, and plugging in, we get the following. So of course the two different area equations must be equal, and that yields this. Now if we look closely, we can see that those eccentricity terms just cancel out, and we can just rearrange this to a formula which dictates that capital P squared is proportional to A cubed. This is Kepler's third law. Now, really, Kepler didn't know about those other terms in there. He just wrote it as a proportionality. So we sometimes call this Newton's version of Kepler's third law. But it's way more powerful because Kepler was only really talking about planets orbiting the sun. But Newton here can apply this formulation to any gravitational bodies in the universe. So this could be other stars, it could be planets, moons, asteroids, anything really. What's awesome about this equation is that it doesn't depend on eccentricity. Your orbit can be as eccentric as you like. You might even have no idea what its value is, but it doesn't matter. If you know just two of the three astrophysical quantities in here, that's orbital period, system mass, and semi-major axis, then you can always get the other. So that's it for today. We did it. We started from Newton and we explained Kepler. I tried to go through this derivation in lots of small, transparent steps so you could really see where everything comes from. I know it can be frustrating sometimes when you're looking at a textbook and they skip over big parts of the derivation. If you have any questions though, be sure to put them down below and I'll try to answer them. I'm also going to leave 3 questions on the takeaway slide for you to try at home. Answers will be in the description. So thank you so much for watching, and make sure you join us in the next video when we'll be diving into 3-dimensional orbits.